Okay, so block 3 and an advert for Iain's YouTube channel. So Google Iain Barton, you'll see eng on the end and you'll get to the OU one. So block 3, typical block 3 question. Again, this is an old example where block 3 is going to be a lot of describing type stuff, isn't it? So here, some sketch type questions. So B and C, I would guess, would be 3 marks these days. The other stuff would be simple definitions, 2 marks. A simple definition for strong and weak bonds. And again, state 2 things there, so 2 marks there. 2 ways in which energy is stored in living cells. Okay, the equations, not much in the way of equations. They remind you for block 3 to go back to your other blocks that you might want to be reusing equations from there. Since all of this was covered, and they wouldn't bother with this, since all of this was kind of covered with your TMA and this, the flow rate with pressure difference, so that wasn't used, was it? Or shouldn't have been. So maybe that's the only real possibility I can imagine. Backing ratio was mentioned and that was used.
Will they give you, will they use the packing ratio and everything in an exam because it's from the DVD? Would they bother?
Well, exactly. So I don't think it's going to. Yeah, I think it'll be descriptive questions. So here we look at some answers for this particular short question. I will skip over this since we're going to break down the problem. But you can see our basic problem with this question. We've got a flow rate. Flow rate coming in, Q2, and 2 other flow rates coming in, volumetric flow rates coming in Q1, Q1. So overall we're going to have a Q2 plus 2 Q1s coming out, and let's have a look at our questions. So laminar, what else could I have answered here? Goes back to the formulas.
It's Reynolds temperature.
Yeah, I could also say Brown's number. I think that would be valid. So streamlines aren't going to get. There isn't going to be any mixing in the streamlines, and things will be uniformly sort of describing it some way like that. Here, part B, define your terms. We take the time to be a variable understood as read or as part of our answer. So x is the distance away that the particle is diffused, and d is the diffusion coefficient. Part C, explain the diffusion, how it affects the profile. So this one, possibly 3 marks. Yeah. We could have something like that the central stream of the flow will start to spread out, so that's why you want to minimize things. To minimize the time available to let something diffuse, okay, that would work. We could maybe maximize the flow rate, or we could just keep things in a short length. So when you think about it, again, if you just thought about diffusion, they're the sort of ideas that you'd come up with anyway. D, suggest one advantage for flow focusing in a microfluidic analysis system. So I've got possibly 3 answers here that I would write down, assume that there's no negative marking, and they'd probably accept 2 from these answers. So there's a typo there, sorry. To enable the counting or sorting of particles in a central stream, so that's what we might want to use it for. To ensure uniform flow velocity. if the detection system uses a laser beam, so we're getting on terms of like how you might change the design, then we could have it to reduce the reflection of the channel cycles. Part E, explain briefly why the maximum flow rate through channel is strongly dependent on the cross-sectional area of the channel, and you had this in your TMA really. So yeah, this did appear in your TMA, that equation. So you could be talking about the flow rate is dependent upon the pressure difference, the rate, oops, sorry about this, I should stop pointing. The radius of your tube divided by the viscosity of the flow and the length of the tube that you're trying to push the flow down. So you can reference that equation as part of your answer, and then you could either go back and talk about that equation and say that the flow rate is going to be dependent upon the radius to the power of 4, and then say maybe double. That's what a lot of people did, didn't they? A lot of people said, if I double it, then that will increase the flow rate by 16 times. Alternatively, a more physical, sorry, that's the answer down there. Or here we've got the answer more based upon kind of like describing the features, the wetted area. You're looking at how much area that you're trying to push down compared to the wetted area on the outside. It's kind of just be descriptive of like that sort of way to try and answer that question. So the stuff that we need to revise in block 3 will almost certainly focus upon the nanobio side of things. You don't have to worry too much about the esoteric names of proteins, and don't forget there's also some that you could reuse if you wanted to in the back of the exam paper. And also the complemented names for such as the DNA, what the various bases are called, and so on and so forth. There's a dozen or so common words that will commonly appear in the exam paper, and here's some examples. Lipid, hydrophilic, enzyme, protein, and so on. Okay, so you need to have a grasp of them and know what they're talking about. You need to be able to describe how things work, and a common one is to talk about pairing, but we've already had that in the TMA, so maybe that might not come up. Then as an add-on, then they have these microfluid dynamics side of stuff. That's always going to be laminar flows, because your Reynolds number is always going to be so low, and might involve diffusion calculation. We've done these two things, so the third one I think is more than likely a candidate for an exam question. In terms of the wings, again talking about the biological side, how the wing bonds work, being able to draw these kind of things, do rough sketches of them, and I think that would be it for the principles. And for the technical side of it, it's probably going to be this guy here, I reckon, that you want to focus for your exam, because you've had quite a lot of fluid mechanics type questions in your TMA. In terms of the DNA, focus on the basics, being able to describe these things, complementary bases, the structure of the helix, how the hydrogen bonds are working, those sort of things I would think that you need to mention. Being able to describe how DNA structures are self-assembled. We've mentioned that again. These have come up in our TMA, so whether these would come up, I don't know. When the strand is linked together, so that's also come up. Maybe they might ask us to talk about programming and self-assembly of structures. That hasn't come up, has it? And this means that we need, so there's this area in your in your book, which I'm trying to recall, it goes on about this kind of negative design process and positive design process. So those are maybe candidates for an exam. So once you've talked about the design, what else? Of the design strands and how that they can be broken up, Brownian motion and so on. So maybe stuff on assembly, I don't think has been covered on our TMA so far. These, well, the top one's been done, isn't it? So maybe doing a sketch of the phospholipid. I think that has that come up or not?
A little bit.
Little,
The first
yeah.
question sort of
So
touched on
that one did, didn't it? Got the bottom. So that would maybe do a sketch of that. 10 marks. And we haven't done.
Nothing
so
on
this.
ATP yet.
So the transfer of energy, ATP to ADP, I think will come up in the words. So how the triphosphide goes to the diphosphide. You could show off again, use the energy in your data, go back to your data sheet, and you could actually mention how much data. I'm fairly sure it's in your data sheet.
Why is ATP unstable then? Is that just to do with the bonds between those phosphate?
Basically, yeah.
Right.
So the fluid stuff we've had, so I would guess that's not going to come up.